Okay, maybe we can get started. So today's lecture is going to cover what I call data-centric evaluation of machine learning models. And really what we're focused on when we say evaluation is actually how do you improve models by improving their data. But of course, improving models really requires being able to evaluate them, which is why we titled it this way. And so this is probably the machine learning pipeline that you've been taught in most of your classes. And you collect data and define the machine learning task, explore the data and figure out what kind of variables there are and pre-process them so that it's suitable for machine learning. And then you train a model, and that's probably what you did in previous classes. So far what we've been teaching you in this class is investigating the shortcomings of the data set. And often in a real application, you would investigate the shortcomings of both the model and the data set in order to be able to improve the model. And then the rest of the typical machine learning pipeline then looks something like this, fixing up the data set to address any kind of issues you found, and then improving the model and deploying the model and monitoring future data for new kinds of issues that might have emerged. And this lecture is really going to focus on this critical step of investigating the shortcomings of the model and data set, as well as some of steps 6 and 7 to improve things when you find problems. And as I mentioned, the main topic that we're going to focus on is evaluation of these models, which is a prerequisite for improving them. And then how do we handle poor model performance when we do detect there's a problem, in particular, a problem on a specific subpopulation in the data, maybe that has low prediction accuracy. And then how do we measure the influence of individual data points on the model in order to attribute back where the model is doing well or not well based on the training data that it was that produced that model. And so let's start first with just a recap of multi-class classification. And this whole lecture will just focus on classification tasks, but all these ideas, like many of the other ideas in this class, will be applicable to most machine learning tasks as long as it's supervised learning. And so just to recap, hopefully everyone is familiar with multi-class classification, given that we've had a couple lectures on this. But we have a data set with n examples, and in each example we measure some features x and a label y, and we assume these are drawn from some underlying distribution over the features and labels. And our goal is to use this data set to train a model that can classify a new example with new feature values x that we might have never seen before. And this model will produce typically a vector of predicted class probabilities where each entry is supposed to approximate the true probability that the label would be given this class k, given an example with features x. And so critical to evaluating all this is the specification of a loss function that scores each prediction from the model. And in machine learning, there's a little bit of abuse of this term in terms of loss function being used to refer to the thing that you're training your model with, like the objective function that you're doing optimization over to select model parameters, as well as the thing that you're using to evaluate predictions of your model on future test data or validation data. And here we're mainly referring to loss function in terms of the evaluation on test data. So this would be analogous to the accuracy of the model, say, in classification, whereas you wouldn't train a model directly to optimize accuracy because it's not differentiable. So yeah, we're always looking for a model that minimizes this loss and expected value over an example drawn from the same distribution, but a new example critically. And hopefully that's all familiar. If it's not, happy to take any questions. But this process has some key assumptions. One is that, as I mentioned previously, that the deployment data will stem from the same distribution as the training data. It's also assuming that the training data are independent and all from the same distribution, and that each example belongs to exactly one class. And we saw in past lectures that these assumptions might not always be true in the real world. So as I mentioned, the loss function is this critical object that is used to evaluate the model predictions for a new example versus the label that was given for that example. And typically the loss will either be a function of the predicted class, deemed most likely by the model for this example. And so examples of that would be like accuracy, balanced accuracy, which is essentially computing the accuracy for each class and then averaging them, which is a better way to have a loss that is not so sensitive to some classes being less common than others. Precision and recall, which are used in sort of medical applications, information retrieval applications, where you care about false positives differently than false negatives. And the idea is all of these losses are really used to evaluate hard decisions that you're making based on your model, because the model is just predicting a single class. It's just saying, I think it's this class, and you're essentially taking that decision as the item that you are evaluating. Second type of loss function operates on the predictive probabilities from the model for each class. And examples of these kind of losses in classification would include the log loss, the AUROC, calibration error. And so these kind of losses actually measure, the probabilistic beliefs of your model and how often those probabilities actually align with the natural distribution of probabilities in your validation or test data. And so one more thing is just those are good, these are better loss functions to use if you're going to make decisions sort of that have asymmetric rewards as a result based on the probabilities from your model. And so when we're talking about reporting model performance, obviously it's not ideal to report just a single number to summarize how good a model is over some diverse population. But this is what everybody does, and it's one of those easy to criticize, but not easy to have much better solutions for beyond showing a bunch of numbers. And so the typical score that people use is just the average of the loss over many examples that were held out during training, which we call the validation set. But some alternatives you could consider is averaging the loss for every example in each given labeled class separately, the per class accuracy, this is called, which would give you a finer grained breakdown of how the model is performing on different relevant subgroups of the data. Or you can actually report the complete confusion matrix of your model saying how often does it tend to predict this class when the true label was this other class, which gives you even more information about the model. But again, it's not as easy to just look at a confusion matrix, which was k by k, and say this model is better than this other model, versus a single number. Everyone likes that because it allows them to more easily compare two models. And so it's really, really important to think about how you're going to evaluate models, and I want to impress that point. People like to jump in to the machine learning aspect and to improving the model right away, typically just using the standard loss. But really how you evaluate these models has a huge impact in real applications, and really at the end of the day that determines what model you will end up with, and what kind of improvements you made only contribute like 30% or so. Probably 70% of the result you get in the end is how you evaluated your models. And that determines everything. And really, so you should be thinking about that as much as you think about the fun questions in machine learning, like what models to apply and how to improve them and what kind of tricks you can come up with. So let's consider, for example, a binary classification task of predicting fraud or not fraud in some credit card transactions. Can anyone tell me why maybe it's not a good idea to just use overall accuracy as our evaluation metric? Yeah.
Most transactions probably aren't fraud, so just training the model to always say not fraud would work pretty well.
Mm-hmm. Any other problems we can think about? Yeah.
It's a bigger issue to mark something as not fraud when it is fraud than the other way around.
Yeah, exactly. And maybe we as the machine learning person don't really know how much of an issue it is. And so maybe it's better for us to use one of those loss functions that evaluates the probabilities from the model, and we can give those probabilities to somebody who actually has some sense of what the costs are in terms of false positives and false negatives, and they can choose a cutoff based on those probabilities, and they can even adjust the cutoff over time. So yeah, this meme is showing exactly the point that you just made. And so I'm going to get into some common issues that arise when evaluating models. One of like the most nasty ones is this failing to use truly held out data, or also known as data leakage. And so this is like, taught in machine learning 101 always, that you always need to split the data, never touch the test data except for evaluating your model. But what happens in the real world is you have some complex data pipelines. The data is being pulled in from all these systems, and it is often just the case that you happen to have duplicate values in your test data. You happen to accidentally have a feature that was perfectly correlated with the label that actually won't be available in the future, but for some reason it made it into your training data. And so, yeah, this is just a really, really nasty problem and hard to diagnose, besides when you see much better than expected accuracy than you would imagine is possible. And there's a big study out of Princeton showing how people are using machine learning in different sciences, and just showing how poor the practice of machine learning has really been in a lot of these sciences, where they're trying to say, now we can predict this based on this, so therefore we have uncovered some interesting scientific phenomenon, but actually a lot of the accuracy is just due to data leakage. This is sort of the new p-value from statistics, which was a big problem for a lot of sciences before. And also, reporting just the average loss really underrepresents severe failure cases for, if you have a really rare subpopulation that's only 1% of your data, but you're just measuring an average loss, and say your loss function is just like accuracy or something bounded, then it doesn't really reflect very well that there's this 1% of your data that's consistently, say, always getting the wrong prediction. And also, as I mentioned last time, the validation data might not be representative of the deployment setting due to selection bias. And so the best thing you can do is just try and always make sure your validation data is as representative as possible to the deployment setting when you're not able to get a whole data set that's super representative. That way you can at least see your model training on one distribution and testing on another, and see what kind of hit it's taking. And then, as we saw in the first and second lecture, obviously some labels might be incorrect, because if we have data labeled by humans, they make annotation errors. And so this is just getting back to that point of data leakage. Like, in many people, when they first get in the field, get very excited when they see 99% accuracy, but as you spend more time in the field, you get more worried the more you see when you start to see 99% accuracy. So now we're going to go to the subject of underperforming subpopulations, but I first wanted to see if anyone has any questions.
Wait,
Yeah.
Can you explain the difference between the first and third issues that you outlined? Is it the first one for validation purposes?
Yeah, exactly. So the first one is about, there is some information. So about each example, like data point, is supposed to be independent of the other data points and independent of the label for the test example, especially. And so this sort of leakage can occur, say, if you have a feature that's very correlated with your labels, only in the training data, but not in the real data. So that's an example of selection bias, yeah. So that's like a special case of selection bias. But then there's just the straight up issue of having like duplicates and things like that in your data set, which is not necessarily selection bias. It depends how they arose. But yeah, often some data sets literally just have duplicated data, and at least you should make sure you split the training and validation data such that the duplicates are all in the training data or all in the validation data, but not half-half. Yeah, that's a good question. So yeah, the selection bias is more general. It's just really saying somehow when you collected the data, you did something that made it not reflective of the real world, which is almost always inevitable. It's just a question of how much of a problem have you introduced. So there was this famous study from MIT, actually, where they examined all the facial recognition software from all the big cloud providers and all the biggest tech companies you know about. And they showed like really, really big disparities between like the accuracy on men with light skin versus dark-skinned women. And these are products that were running live, so presumably they had gone through a lot of testing, and it's kind of interesting that nobody had discovered this. And so, yeah, this lecture would hopefully teach you how to discover this sort of thing, so that if you launch a product like this many years from now, you wouldn't have similar issues. So here we're going to talk about a slice of the data, which is a subset of the data set that shares a common characteristic. And this is, in many different fields, referred to as different things, like a cohort, subpopulation, subgroup. I'll try and use those terms interchangeably. But some examples would be data captured by one sensor versus another kind of sensor. That makes the data from this one sensor all have a common characteristic in your data set. Or maybe you're getting data from one location versus another location versus another, and so all the data from each location is sharing some kind of common characteristic. Can people think of other examples for like human-centered data that might be ways to define slices that are meaningful? Yeah. Yeah. I should say, when we're thinking about slices, these are typically things where we don't really want our model's performance to vary too much across them because we kind of expect them not to play a big role in the prediction problem. Yes?
You gave an example versus X in the previous one.
Mm-hmm. Yeah. Yeah, so one way to think about this is like anything that on a job application you shouldn't base a decision on. You probably also don't want your model's predictions to really be based on. And so another question I have is, given I said we don't really want our model predictions to depend on what slice a data point belonged to, do you think we can just delete all the slice information from our data set and from the feature values and then say we're good because this information is no longer in my data set? Yep.
It would probably be hard because it might do something like with the cow example where it learns things that might correlate strongly with the cohort or size.
Mm-hmm.
And then it would use that rather than the actual.
Exactly, yep. So a lot of the other features that you leave over in the data set might be correlated with the slice information, and then your model's still going to depend on information from the slice, just not explicitly. And so it's actually better to keep it and analyze what's going on with the model over the different slices. Did somebody have a question? So let's now talk about improving the performance of our model for one particular slice of the data. And so here we're assuming, say, the data just has like J slices that we know. For example, let's say it's sex in a human data set, and we can see the information about each person. And so we can just analyze what is the loss of the model on each slice. Let's say we're just using the average loss over the subset of the data that belongs to that slice. And so now we've seen there's a slice that's doing poorly, and the question is, how can we boost our model for that slice? And so in this example, let's look at a binary classification data set. And here the two classes are red versus blue. And one way to improve performance for a particular slice is simply to just use a more flexible machine learning model that has higher fitting capacity. And the reason I'm showing this example is because this is an example of a data set where if you were to fit a linear model, it just doesn't have enough capacity to fully fit the data. And therefore, the linear model has to make a trade-off of what examples is it going to give high loss to, right? Some of these examples are inevitably going to not be predicted correctly because this data set, the relationship is nonlinear. And so you'll see that many different linear models actually would work pretty well or would work somewhat equally well for this data, right? Because where the decision boundary is, it's sort of just going to be like a vertical decision boundary. And if it's vertical versus if it's horizontal, you'll get much different performance for this slice of data on the left there. And so, there's not really a way to fix that easily, but you can note that you could control that with your linear model by choosing a different linear model. And I'll get into that in a second. But the easiest way for this sort of data to avoid having the performance hit for a particular slice is just to use a more flexible model, like a neural network type model or a nonlinear model with higher capacity that doesn't have to make the sacrifice of hurting performance on this one subset of the data while not hurting it on the other subset. It can just say, let's try and boost the performance over all the data. Another common way to try and improve model performance for a particular slice is to, if this is a like minority subgroup of the data set that has much fewer examples, then we can try and oversample them or upweight them if we're using a model that can take in sample weights. And basically, yeah, just make the model think that these examples are more important because there's more of them, or we've explicitly increased their weight in the fit. Yep.
Isn't an issue with doing something like this that you could sort of overfit on the minority subgroup, and so you get like overfit thing, but an overfit fit that's like kind of bad on a minority subgroup that you wouldn't get on the general subgroup?
Yes. So here, when I'm talking about improving the model performance for a slice, I'm always assuming we have evaluated it on some validation data. And for now, I haven't been considering the case where we are, changing the validation data too. So hopefully you'd be able to detect this kind of overfitting because you have the validation data. But what you're saying is, of course, totally right that if the minority group is really rare, it's also rare in the validation group probably. And then how do you deal with that is another question. Typically there, you would try more to deal with it by reserving more of the minority subgroup for the validation data, but not oversampling it in the validation data or anything like that, because you don't want to skew your metrics. Yeah, so to see why upweighting one subgroup might help, here we have data from two classes, and it's overlapping in the feature space. Say these are just two-dimensional features. And so there's actually no way any model can predict some of these data points, correctly. It always has to trade off, do I favor making a prediction for the blue class or for the orange class? It's just fundamentally a trade-off that the model has to decide on. And so by upweighting the minority subgroup, you're just encouraging the model to make the trade-off more in favor of the orange subgroup. Another thing you can do that's probably ideal is to just collect additional data from the subgroup with poor performance. Of course, this is expensive, and so this is also something you want to see if it might have promise first before you just dive in. And so going back to the lecture yesterday where I taught about extrapolating the performance of a machine learning model, we can try and do that, but now just fitting the model to subsets of the data where we've only downsampled this subgroup relative to the rest of the data to see sort of as the proportion of this subgroup grows in the overall data set. And then if we extrapolate that proportion to even higher relative values, does the performance of the model seem to be improving for that subgroup as well as for the overall data set? How is it getting worse or better? Yep, and there you might often see a tension between the performance starting to get better for that subgroup as you get more and more samples from it, but the performance for the whole group overall might actually start to go down if we're in a scenario like this. It's really dependent on the application. Another thing you can try and do is measure or engineer extra features that allow the model to perform better for the slice where it's currently not doing well. So obviously, if you can measure extra variables about your data, that's always great if they provide some information that's useful for predicting. And sometimes you might be able to measure certain things that are more useful for one slice than another. So you might not have considered adding them to the data until you realize that the model's not doing well on this subset. So an example here is classifying, say, if a customer will purchase a product or not based on customer and product features. And so maybe the customer features are based on the history of that customer, right? In your e-commerce website or whatever. And so predictions for new customers or young customers might be worse because you just don't have much history about them, so your features for them are not as informative. And so one thing you could do is just explicitly engineer extra features to the data set. So this is not even requiring you to measure extra information. It's just you as a data scientist are taking the data you're given, creating features using your own ingenuity that you think will help improve the performance for this specific subgroup. Like here, you might add a feature that's, say, popularity of the product among young customers specifically, and that could boost the accuracy of this classifier for this slice. Okay, so previously I was talking about the situation where you have, say, J subgroups in the data, and you were just measuring the model's performance on each one, seeing where it was doing badly, and then figuring out how can I try and improve the model for that subgroup? But in many data sets, we might not even know what the relevant subgroups are, right? Like in an image data set like this, what are the relevant subpopulations that we should be thinking about if we wanted to go through the previous process? And so a high-level strategy that one can use to discover these sort of underperforming subpopulations is to sort all the examples in the validation data by their loss value, then look at the examples with the high loss where your model is making bad predictions, and then finally apply clustering to just those examples with the high loss to figure out what are some patterns amongst these examples which are all receiving bad predictions from the model currently. So irrespective of discovering underperforming subpopulations, step one of sorting the data by loss value is always a good idea. Whenever you've trained a machine learning model and you want to start thinking about how you might improve it, it's always good to do that and just see what kind of data points is it making bad predictions on, because those might be mislabeled. There might be all kinds of reasons that I'll get into. And this is often referred to as error analysis. But then once we've done that, we want to see what are the common patterns amongst these examples. And so a natural way to do that is through an unsupervised learning technique called clustering, which intuitively just tries to find subgroups, exactly subgroups amongst these examples. And so if we just restrict ourselves to only those examples where the model is already doing poorly, we should ideally be able to find clear subgroups where they share a coherent theme and the model is doing poorly to identify a factor that's responsible for this poor performance. So here is an example of this. This method is called domino, but it's just a specific instantiation of the idea I talked about, where you have your image classification data set, say, on the top left, and you have some images in a forest, some images are with a blue sky, and that would be sort of maybe you discover that your model is, or you don't discover this, but your model is actually performing poorly on images that come from a blue sky. And so if you were to sort all the data by their loss and then apply clustering, maybe it would just naturally be the case that a cluster of blue sky images emerges amongst your clustering in the data with high loss. Another thing you can do that's a little more advanced is make the clustering label aware, which is what this method proposes, so that you're specifically emphasizing that the clusters should also all have the same labels to make even more coherent clusters in classification tasks. And so then, once you've discovered, these subpopulations and you've decided they actually are meaningful, you can just go back to the previous slides and think about how you might improve the performance for each one that is particularly worrisome to you. So now we're going to get even more micro and just focus on one particular data point rather than a subgroup, and ask why is the model getting this one prediction wrong, and how can we improve things. And so again, going back to the first lecture, maybe the label is just wrong and the model was actually right. And so the best thing we should do here is just correct the label in our data set. Or going back to the first lecture, the example might not belong to any of the classes at all, or be fundamentally not a predictable example, like if it's a super blurry or super dark image. And there we might consider just removing this example from the data, or we might even consider adding an extra class like an other or clutter class we saw before to the data set if we see many such examples. And we also expect them to recur at test time during deployment. So another common issue is the example is an outlier in the data set. Like there are no other similar examples in your data. Do you guys have ideas on what we might do for such an example? How might we try and improve our model? For example, here we have a bunch of images of clothing. Maybe we're at e-commerce, doing some e-commerce machine learning, and then we have an image of a 3 in our training data for some reason. Yeah?
I guess it depends if it's something that's actually possible. Because, like, the 3 is something that we probably should just remove from that data set. But if it's just an extremely rare event that is something that could happen, we don't want to just do that.
Exactly, so it's subtle. Yeah, this is not an easy answer. So if you would never see this similar example during deployment, then you can probably just get rid of it. Otherwise, you might actually want to try and collect more data for this. So going back to the first lecture and the Tesla example, they noticed the car was doing badly in tunnels in that data engine that they had. And so they they weren't even training their model on all of their data because they had too much data, but then they purposefully went through their massive data set and looked specifically for tunnel scenes to increase the number of tunnels in the training data. Another thing you can actually do is, so often you're not going to be able to collect additional data, right? If you're the machine learning person and you don't have the ability to go collect additional data, you have to apply some kind of data transformations at that point. And so one data transformation you can try is to just make the features look more similar to the model across outliers and non-outliers, such that the model is not going to produce such an unreliable prediction for this outlier. And so if you have like numeric features, you can try normalizing them to a common range via like a quantile normalization is a common one. Or you can actually delete a feature entirely, which sometimes you'll just have one feature that's causing particular data to be seen as an outlier by your model. But actually, the model would do fine if you just had removed that feature from the whole data set. Another thing you can do is add synthetic data. So the model starts to become less sensitive to the difference that makes this outlier stand out from other examples. For example, if you had, maybe an extreme example is if you had black and white images and color, and 1 or 2 color images in your data set, and those are huge outliers now, you could turn all your black and white images, you could colorize them or turn all your color images black and white, and then basically those images become less outliers in the new representation of the data set. And then finally, you can upweight or duplicate the outlier if it's a really important example and you really need to do something critical with it. Then, duplicating it multiple times in the training data is a very simple strategy, and a good way to do this is to actually try and change the feature value slightly each time you're duplicating it, so your model is better able to really capture a pattern around this example that it learns to predict more stably. And when you're creating these variants of the feature values, we will have a lecture on how to do this properly via data augmentation, but the key idea is not to add too much variation such that you would expect the label to change. You want to add just a little enough variation such that you still expect the same label to apply. Okay, another reason why the model might get a particular prediction wrong is the kind of model you're using is just not ideal for this kind of data and these examples. And so how can we diagnose this? This is similar to going back to what I just presented when you have an underperforming subgroup and you're trying to see if you can get more data from that subgroup to improve the performance. Here you're just trying to see if you forced your model to really focus on just this examples and examples like it, would the model even get better or not? And so here you can try upweighting similar examples to this example or duplicating them a bunch of times in the data set, retraining the model and seeing if now the model has gotten better. And if it's still not better, you might really want to try a different kind of model if you're worried that you really want to get this example's prediction correct. And so this is kind of a model-centric approach as well that you might consider, where you fit different kinds of models, you do hyperparameter tuning, you do feature engineering. But really, this is obviously a problem with the model when we say the model is not a good fit for such kind of examples. Another reason that can happen is the data might just have a bunch of examples with almost the same feature values as the current example that your model got wrong, but those examples all have a different label. And so in that sense, there's not much a model can do. It's got to get something wrong. If there's you can imagine there's 2 identical data points in your data set and they have different labels, one of them will inevitably be predicted incorrectly. And so going back to the first lecture from the example from ImageNet, it has this keyboard class and this spacebar class, and the images from both look very similar, and so inevitably some models will just have a non-zero loss on certain images from these 2 classes because each image is only given one of these 2 labels. And as we saw before, one thing we can try and do here is define the classes more distinctly to give a much clearer, we can tell our data annotators to, when they're labeling the data, we can give more clear definitions of what this class is versus this other class. Or we can merge classes such that the remaining classes are more distinct. And then another thing we can do is measure extra features that actually enrich the data set and make it such that now when you have two examples with different labels, they almost never have identical feature values because we've actually measured some new feature of the data that actually discriminates these two. Any questions on this? So yeah, these are 5 different strategies for trying to really boost performance of a model just by inspecting it at a very local level on the level of individual prediction. So you'll typically sort all your data by the loss that the model's incurring on it, and then go through this exercise in your head. It's typically better to start with the subpopulations first because those are big groups of data where improving your model for those can actually lead to meaningful changes, more meaningful changes, I should say, than improving the model for individual examples. But sometimes the individual examples really tell you a lot and actually can make a big difference, especially if there are certain high-stakes scenarios in your application that really matter. Okay, now we're going to shift gears slightly and talk about the influence of individual data points on a machine learning model. And so one way to think about this topic is imagine you have people selling you data, and maybe you're doing medical machine learning, and these are hospitals or patients, and so their data is actually really valuable, and you are going to use that data to train a machine learning model that is used in some application that makes you some money. And then the question that might be natural is how do you give that money back to the people who gave you data? Obviously, one way to do it is just give everybody the same amount of money for each example that they give you, but that might not reflect some of these data brokers who have very unique examples that are actually much more valuable to you and maybe higher quality. For example, if they have less label errors in their data, you might consider paying more for that. And so this is really a fundamental question. And it's also a challenging question because you can imagine the value of the data really depends on the other data, right? Like some data might be super useful, but if all the other sellers have the same data as well, then it suddenly starts to become less useful to you, or maybe you're not going to pay as much for it. And so this is a key question that has been studied a lot in economics, just in general, when you have a bunch of people providing some kind of input, how do you allocate profits back to the people? And what kind of desirable properties do you want in such allocation schemes? And so a really simple form of this that is pretty popular is to just ask, how would my model have changed if I only omitted a single data point from the data set, retrained the model, and measured how much did the model change as a result? So here, there's 2 kinds of change we might be interested in. One kind is how did the predictions of the model change as a result? And another kind of change we might be interested in is how did the accuracy, say, on some validation data change as a result? There's also a third kind of change, which is like how did the parameters of the model change as a result? But that's less interesting to folks nowadays where most people are using sort of neural network type models with less interpretable parameters. So yeah, mostly focused on some kind of function of the outputs changing as a result of retraining the model on a different version of the data set where you dropped one data point. So here we have a 3-class classification data set where, say, we've trained a model in this data set and it has 98.5% accuracy on our validation data. And then let's say we drop the data point, the most right data point here, and we retrain this model, and now it gets, say, 98.3% validation accuracy. And so you might then conclude, basically, that the impact of that data point is something like 0.2%, right? That's sort of its contribution to your model. And that's a natural way to think about things. Can anyone think of like why this might not be sort of the end-all, be-all of valuing data, and why what issues some people might have with this form of data evaluation. Yeah?
Maybe it's something that you could consider to be part of like a core set,
Uh-huh.
where it really instructs like the structure that the model should be learning. And so if you were to pull it out, you would lose a lot of the structure that the model is learning. And maybe the reason that the model even did as well as it did in the first time, it predicted it very well because it has everything that the model needs to predict on.
Right. Yep, so that's a good one. And the idea of this set of data, maybe like that data point alone is not impacting your model hugely, but it with 10 other data points together are collectively having a big impact on your model. And so, yeah, that's a key idea that this leave one out influence doesn't really capture. You can imagine in the extreme case, we have 10 data points. They're all duplicated, but they're all actually very important. Like they cover some rare issue in our data set or some rare class that's not very common. And so if we delete all 10 of them, suddenly our model is much worse at predicting that class. But deleting any one of them is not so impactful because there's actually 9 other data points still in the data set. And so there's this idea of the Shapley value, and this is basically from economics and game theory. As I mentioned, it's a way to evaluate, to provide value, or to attribute value. If you have a bunch of coworkers and you're on a project, how do you decide how much of the profits from this project should you allocate back to each coworker? And it satisfies a number of desirable axioms. And for example, one axiom that's nice is if you add an additional person to your set who doesn't contribute anything, you want to make sure that the returns to each of the existing people is the same. And then you also want to consider how each of these coworkers is contributing in the context of the other coworkers. And that's the same for these data points. So here we want to consider how is each data point contributing in the context of the rest of the data points, but not only of our original data set, right? Here we just dropped this single data point, so we were only measuring how much is this data point contributing in the context of this particular data set that we happen to have. But that's kind of arbitrary, that we have that data. And so actually what is a more relevant question is how much would that data point contribute in all sorts of hypothetical data sets? And so one way to measure that is to compute this leave one out influence of the data point in some subset of the data set that contains that data point, right? Again, we're just removing it from that subset and seeing how the model changes if we were to just train the model on the remaining subset versus the subset including that data point. And then we can average these values over every single possible subset of the data set. And that gives you a pretty broad understanding of how much does this data point contribute in different contexts where it could have been present or absent from a data set. Of course, this is very nasty to compute, so I'll get into that in a second. But just to see sort of the advantages of this, imagine you have 2 identical data points in a data set, and actually if we delete both, then this is going to really harm model accuracy, but omitting just one of them won't. Does anyone have an idea sort of what the leave one out influence for these 2 data points would look like versus this data Shapley influence?
Like
Yeah.
the leave one out influence would be very small.
Mm-hmm.
The data Shapley would be larger because you have some subsets where there's only one data point, right?
Exactly. Yep, so leave one out influence will be small. Just because I said omitting only one of those data points does not lead to a big degradation in model performance. But the data Shapley, so for each of these possible subsets, basically half of them will not include the other data point. And so for all of those, when we remove the remaining data point, you're going to see a big drop in performance, so 50% of the time. So then when you're averaging over all possible subsets, you are just going to get a pretty big loss in accuracy. And you can see that this is a natural answer to this sort of ill-posed question of how much is this example contributing to my model? Because here, yeah, you're really considering a bunch of contexts and asking how much is this example contributing in each context. So here I'm going to talk about computing these influence functions. And so as I mentioned, computing either of them is not very feasible, right? Even the leave one out influence, to compute it for a whole data set, you would have to delete each data point, retrain a model, and evaluate it. And if you have a huge data set, that is not going to be very fun. And then the data Shapley, you can basically forget about because you are trying to average something over all possible subsets of your data set, and each of those involves a retraining of your model. So yeah, that is not probably going to happen in any meaningful application. And so here I'll just go to the board. So we can imagine we have a big data set here. And this is our full data set, training data set. And then we have a validation. This is our validation data. And so what we can do is we can just draw subsamples of this data set. And that gives us a subsample data set. And we can do it again. And say we do it 4 times. So now we've got 4 subsamples of our data set. And what we can do is we can train a model on each one and get some kind of accuracy on the validation data. So say training a model leads to and say training a model on this subset leads to accuracy 80%. A model on this subset leads to accuracy 85. And say on this one, it's 70% accurate. So now we have 4 subsets of the data set, and we have the accuracy for each one. And now let's imagine we are trying to quantify the influence of this data point right here. How might you do that, given this information in a pretty straightforward way? Anybody have?
Average accuracies of the subsets that have this point and the ones that don't have this point?
Exactly. Yep. So we can just look at where, say it's present in this one, and say it's present in this one too, but it's not in these 2. Then basically we would just take the average of these 2 accuracies, and then we can subtract off the average of the other 2 accuracies. And that can be our approximate measure of this data point's influence. And so how many times are we going to have to retrain a model to compute the influence of all the data points in our data set this way? 4 times, yep. And so you can see it really depends on how many subsets of the data are we going to draw. And if we want to compute the influence of every data point, and we want to retrain the model as few times as possible, does anybody know how should we choose our subsets to get to that? Yep.
Splitting the data in half each time.
Yeah, exactly, or partitioning it, right? Yeah, so we want to partition it so that it's not, so that we have non-overlapping subsets of the data, and then we're at least guaranteed this data point will be in one of those subsets so that we can even compute this equation, but it'll be very brittle, right, evaluation of the influence because that data point you're basically going to be measuring the effect of the whole partition because that whole partition is either present in the subset or not present. So this is not actually a good way to do it. I'm just asking conceptually. This is the minimum amount of retraining you would need of your model to be able to compute influence for every data point. And just to be clear, the accuracy there could be replaced with any evaluation metric of interest. And then if we were interested in how are my model's predictions changing rather than the loss changing as a result of including this data point or not in the data set, you can just measure the predictions at every single data point in your validation data set and measure how much are the predictions changing for each of these subsets, but it's still the same strategy. And then I also want to just briefly mention that for some kinds of models, you can actually compute these things in closed form rather than this Monte Carlo approximation. And so in statistics, linear regression is the most famous model, and this is corresponding to a regression task rather than a classification task with a mean squared error loss function. And in that world, the leave one out influence is just called Cook's distance, and it's like a very famous diagnostic that people use to check, is there data points you should be worried about in your data set when you're fitting a linear regression model. In science papers, they always do this to check the data, and then they consider removing some of these high influence points if they seem suspicious in some way. And then a recent breakthrough that was made actually was that this can be done also pretty efficiently for classification. So this doesn't work for linear classification with like a logistic regression model. There is not really a closed form analog of Cook's distance. And that's because the only reason you can compute the influence via Cook's distance in closed form is because the parameters of the linear regression model are a closed form function of the data. And therefore, mathematically what each data set will translate into parameters of the model, as well as predictions from the model are closed form. And therefore, you can also recompute, if I were to delete something, just through that formula, how would the parameters have changed. But for logistic regression, there is no analogous closed form solution for the parameters of a model. But for a k-nearest neighbor classifier, there was actually an interesting, very complex algorithm recently invented that can do this in order n log n time. And so a strategy that one can use now in practice, besides that Monte Carlo strategy I mentioned, is if you have, say, image data or some complicated data set, you can take a pre-trained neural network and get embeddings from the data, and then fit a k-nearest neighbor classifier on top of those embeddings. So the problem with fitting a k-nearest neighbor classifier on the original data is it's really hard to measure the similarity, say, of two images in a semantically meaningful way. But in the embedding space, typically these pre-trained models are able to embed images in a feature space that's where the vectors have more close similarity based on semantics. And so then if you fit a k-nearest neighbors model in that space, you can actually then go and compute the influence for each data point and actually attribute, which images are sort of most influential in my data set. Yeah, so you should, if you're able to approximate influence, you should always try and inspect, the most influential samples in your data, and those are the data points that have the greatest impact on the model. Especially if you compute the influence with respect to the model's predictions, that's really telling you exactly, if I had not had this data point, how would my model's output have changed? Like literally, how is the function my model has learned changing as a result of this data point? That kind of information is not always as strong when you're measuring the loss version of influence, like you're measuring how did the accuracy of my model change. Because even if the function changed a lot that the model's outputting, it can sometimes still have a similar accuracy. And so correcting a mislabeled data point with high influence can boost the model accuracy, say, much more than correcting a mislabeled data point with low influence, where that data point actually isn't even contributing much to the resulting model's function that it's learning. So even if I change its label, it might not make a big difference. But the issue with just using influence, of course, is that if we sort only by influence, we might not find, say, the mislabeled data or the data with other issues, because sometimes you're just finding really good data when you sort by influence. And so you can try sorting by influence as well as other strategies like confident learning to sort of find the intersection of both high influence and data points with other kinds of issues as a way to improve models. That's all I have, so any questions for me? And today's lab will focus on basically your creativity going through any of the strategies we presented so far to just try and improve a model on a given data set where the training data is more noisy than the test data. And it's not going to be like a simple fix like you had in lab 1. You actually have to use some creativity to try and improve the training data in some way. And the goal is to just improve the model only by changing the training data, not by changing the model itself. So we just give you some modeling code, and you're just supposed to rerun that code every time you change the data. Cool. I think we can call it if there's no questions. Thank you for coming.